Parallel and larger than memory processing. So what we mean here is when we want to do a collection on some whole big range of OCI or Harper spectrogranules, anything, obviously doing some sort of computation on an entire collection of our remote sensing data set at once is not something we're going to be able to do. That's kind of what we mean by larger than memory. There's more data than we have memory for on one computer, even on a bunch of computers. So somehow or another, the task that's before us is to figure out how to break down a big computation into small computations, so one big job into many little jobs, and then figure out how to put the results of that computation back together again into the big array that we want. So the things that we're thinking about and trying to use efficiently when we're doing that are memory, the RAM, and so that's the one of those choices that we make every time we start an EC2 instance in CryoCloud is we're looking at RAM. And the other thing is CPUs. We want to make sure we're maximizing efficient use of the CPUs that are available as well. Yeah, so both of those things are sort of playing off each other. Even if you could fit that entire collection of OCI granules in memory, that still may not be the most efficient way to do it because maybe you might be running a process that's single-threaded. It's only taking advantage of one of the processors when in fact you have a few. Or once you get into machine learning, it may turn out that you have a whole lot of processors if you're using a GPU. And so this is where it starts. You start having to think a little bit more about some of the computer science side of things, but hopefully as little as possible. And so one thing we're gonna look at today is a package in Python that makes it so that we can think about this as little as possible, so that we can just move ahead and do the science we're interested in doing. So the learning objectives for this tutorial. Oh, I better put on my timer. Learning objectives for this tutorial are to, at a sort of basic level, we're kind of just a little preview here, is to understand the importance of using high performance functions and to do array operations. So we have to understand the importance of using compiled functions and sort of like the good stuff that comes with NumPy and things like it, instead of writing our own for loops, as fun as writing for loops is. We want to avoid that when we can, and we'll do a little demo. And then we want to see so what is Dask? How do I use it? And we'll play around with Dask a little bit on some simple examples. And then we're going to try to apply what we've seen with Dask and really put it all in the background. Because what I want us to see is that a lot of that stuff with Dask, because of its tight integration with Xarray, happens in the background. So we'll do, like I say here, one method for interpolating level 2 swath data, what we've all been working with and struggling with, to a map projection. One method. There's multiple methods out there, and I want to mention that I may not be the best person to know the right way to do this, but it's a workable way to do this that uses Dask. So that's why we're doing it this way. OK, so here's our list of imports. A lot of these things are pretty standard. There's a couple other packages that I think we might be importing for the first time. So I want to make them. This tutorial isn't about them, but I want to make sure that you're aware of them because they're very important for geospatial processing. Any kind of science processing, of course, relies on SciPy. We've probably interpolated it for something, but I can't remember. So it's basically a giant collection of useful numerical methods that are anywhere from what we're going to do, which is we're going to use one of its routine for doing interpolation, but it knows all of the crazy polynomial functions. It can do optimization. It has a ton of stuff. So you'll definitely be using SciPy. We'll use Numba, not NumPy, Numba. Numba converts what we write in Python into something that runs faster. So Numba can be your friend, but it does not solve most of our problems. But it can sometimes. And then another one, sort of out in left field, PyProj. This is the Python projection, just a Python wrapper around the Proj database. Well, it's a database and a collection of algorithms that are used for doing geospatial transformations of coordinates. So PyProj shows up a lot when you're starting to do, when you're trying to do things moving between two geospatial coordinate reference systems. You're basically always using Proj, and in Python it's PyProj. A couple other things that we're not using, but something totally worth being aware of. SatPy is an interesting sort of like it's a Python package, and it actually is also it has kind of some associated packages that depend on it that they're all co-developed together. And one of those is called PyResample. So that's a great library for doing geospatial operations, including resampling. It takes special readers, and nobody has written a reader for any PACE data files yet that I know of, so we're not quite able to use SatPy until somebody develops a reader for our new data. So that's one. And then another one, of course, a lot of times if you're doing basic operations for geospatial stuff, you're using GDAL at a low level. GDAL is a fairly low level that backs a lot of geospatial transformations. And several years ago, they did introduce a feature for handling the kind of swath data, for doing resampling, what they call it warping on swath data using what in their language, well, in our language, is geolocation arrays. You know, we have these arrays of latitude. We have a latitude variable that's a two-dimensional array and a longitude variable that's a two-dimensional array. Those are what they call geolocation arrays. And you can do it in GDAL. It's pretty low level. But for some reason, that hasn't been released in Rasterio yet, which is a package that's kind of the friendlier Python interface to using GDAL. I'm not sure why. It hasn't been released in that yet, so we also don't have access to that GDAL functionality through Rasterio yet. These things seem to kind of like percolate fairly slowly through the geospatial Python packages, as I've seen. So it's always good to know how to do things with the very generic functions like stuff that we get from SciPy. So that's what we're going to do today. We're going to do something with SciPy. Okay, so what are we going to actually try to do once we get to it? We're going to look at chlorophyll. We're just going to take a whole bunch of swaths of chlorophyll over a small region. So we're going to think like, okay, well, let's just focus on the Chesapeake and Delaware Bay. Like, define a little bounding box there. Find all of the granules that OCI has so far. We're not going to process all of them because I didn't want to take all that time. But find all the granules that OCI has so far. We've got all the level 2 chlorophyll products. And take that small box around the Chesapeake and Delaware, project them all to the same coordinate reference system, and then we'll have them all in a nice three-dimensional data cube. We'll have time, lat, and lon in a nice clean cube, but we have to do that projection step to get them all on the same coordinate reference system. So just a reminder of what that looks like, right? These data sets are the ones that have number of lines, pixels per line, but then they have a longitude and latitude variable in there, but we can't quite slice by it yet. And since we're using swath data, we're not going to filter out, we're not going to use the cloud filter at all. So we're going to have swaths like this one that just have maybe a couple values in this region that we're looking at. So a lot of their swaths really won't have very much data. But we're not using the cloud filter because the cloud filter, applies to everything. So maybe there was a lot of clouds in here, but I don't want to ignore a granule that's 50% cloud cover because maybe that 50% clouds is all over here, right? So we're going to just use everything. Got a couple little helper functions here that we'll see how they use below, and then it's just always a good idea when you do anything with random functions, if you want your notebooks to be reproducible, to seed your random number generator. So here we're seeding our random number generator because before we get into the data, we're just going to play around with some random numbers to learn about performance and what it means when an array is big and what we do with a big array and how we split it up and those sorts of things. So a very, very basic level consideration before you start worrying about parallelizing and memory and that kind of thing is if you're worried about performance is to just check and make sure you're using, make sure that you're using compiled functions. And I don't mean like check your functions and make sure that they're compiled. That doesn't really make any sense. I just mean if you're writing things sort of like in Python for loops and it's not vectorized, it's not doing a computation on a whole array, then that's probably that's your lowest hanging fruit right there. If you can figure out how to do that with a higher level, with a compiled function, then you'll be better off. Now, a lot of the times we do things in for loops because we're not aware of the existence of sort of like a pre-built function that can do exactly what we want to do in a vectorized way. So part of it is learning about that, and so like the second thing you're thinking about is maybe not can I do exactly what I want to do with compiled functions, but can I use the existing compiled functions in some way to go through this split, apply, combine pipeline where I split up a big data set, apply some function to it, and then combine the results together. for the performance benefits, it might not be exactly what you want, but there might be ways to tweak it. So that's kind of what you're thinking about. OK. What then are compiled functions, and is there really a big boost to that? One thing that's kind of fun is that we can see what that boost looks like by using the Numba package. So this is just going to be a little brief preview of what Numba does to show you that it's there, it exists, it might be a tool you want to look at some time. But this then example is something of like me doing a very basic, here I am writing a numerical algorithm to calculate the mean of an array. And I do it in a for loop. So I go through and I just total everything up in my for loop, and then I divide it by the number of things, and I've calculated the mean of my array. And we can use this little command in Python, this Python magic, time it. %% time it is a little Python magic. And what that's going to do is it'll run the cell a whole bunch of times. It runs the cell a whole bunch of times and sort of like keeps track of how it times it every time. It keeps track of how long it goes. And we find out in the end that this thing, on an array of 10,000, what did I do? I just did a range. I didn't even do a random number. 10,000 numbers, it took it 500 microseconds more or less to go through. So that's what the time it thing tells us. It took about a half a second to go through something like this. And this is an example of me writing a for loop that's probably not going to be very slow. If we want to turn that into a function so that we can then get a compiled function out of it, we'll start by defining the function. I'll do something a little bit more complicated just to sort of like think about this idea of, is there a function that does exactly what you want to do? And there is not always a function that does exactly what you want to do. So we're going to do a function that calculates the mean and the standard deviation simultaneously, right? So we're going to try to go a little faster, save a little time, and calculate the mean and standard deviation simultaneously rather than doing it in two separate function calls to NumPy and see if we can beat NumPy. So we have a little function that does that for us, but it's just a Python for loop. We can check that it does it, and what we're doing is here we're just generating a random normal distribution, and if it works, then the mean and standard deviation should just give us the parameters back. So a normal deviation with a mean of 1 and a standard deviation of 2. With a sample size of 100, we get a very poor approximation, but obviously if we do a much bigger sample size, then we would get a much better approximation. So we can try doing that, going back to a sample size of 10,000 and seeing what happens. And if we time our function as our baseline, we can see it takes between 2 or 3 milliseconds to calculate the mean and standard deviation on a sample size of 10,000. So sort of like that's our baseline in Python. That's what we did. Numba has a routine called, or it generally does this thing called just-in-time compilation. That's why the function we're using here is called njit. It's just-in-time compilation, and the n is just, I don't know why it's n, but it's a prefix that says, look, Numba, if you can't compile this function for me, then give up. As opposed to returning me a function that still works but isn't any faster, it says actually raise an error, give up if you can't compile this into something fast. And what does that really mean? Why am I saying that we have to compile this function? We talk about the difference between a language like Python as being an interpreted language and a language like C, C++, Fortran. Those are compiled languages. This step of compiling just means translating something that's human readable. So whether I write in Python or whether I write in C, I'm writing human readable. When we compile something, we translate it into something machine readable. So it's a low-level language that then the kernel of your computer can read and do the computation. It's not something a person would ever read or write directly. That's what compilation does, and the important part is that when you compile, it kind of has to know what the data is that's coming in. And so that's kind of the trade-off. So like when you are writing a compiled function, it has to know what data to expect. When we write a function in Python, it doesn't know anything about what kind of data we're going to give it. We just define that function and merrily go on our way without worrying about it. So Python has some trade-offs. It's more flexible. It's easier to program. It can be slower. There's a performance cost there. So we give our function, the one we wrote, mean and standard deviation. We pass that function into njit. So the just-in-time compiler gets the whole function, and it gives us a whole function back. So compiled mean and standard deviation is then the whole function back, and we can try it and see what it does. The actual compilation step doesn't happen until I use that function once. So that's why, that's what I was saying, like it needs to have seen the input data before it actually does any compilation. That's how it's going to work. So it has to be called once on some data. But then you can change the data. You have to give it the same type of data, but you can change the data, and you'll still get that performance boost. And when we do it, so now that we've called it once and it's compiled, we can see that this compiled version, all I did was pass it through Numba. And now it takes, what was it, 15 microseconds. So it went from 3 to 4 seconds, or 3 to 4 milliseconds, I think is what it was, to 15 microseconds. So it's a very, very big speed up. But it took us a lot of time probably to figure out how to write our little method for calculating things. And then we had to make sure we had our NumPy algorithm right. This was a very simple one. So the question is, well, what if I just used the close approximation that we already get from NumPy? These are NumPy arrays. I can just use mean and standard deviation. Maybe it's not calculating them simultaneously, so maybe we're doing some duplication here in our effort. But still, it comes out as 40 microseconds. It's a little bit slower, but for me, that difference is where it's like not enough of a difference to make it worthwhile for me to sort of like develop my own Numba function and use it that way. So a lot of the time we will have the compiled functions available for us. They might not do exactly what we want. Hopefully you'll be able to do your thing using existing NumPy operations. And if not, you do have Numba sort of as something else that's in your pocket. And then the other reason that living with what NumPy can do, rather than starting to develop your own functions with Numba, if you live with what NumPy can do already, then we immediately have our step into using this bigger framework for doing parallel and larger than memory computations using Dask, because Dask is in many ways a re-implementation of everything that NumPy can do, but it re-implements it in a way that it can handle this concept of split, apply, and combine. So let's talk more about what that is. Any questions about, that's all I'm going to say about Numba and compilation. Does anybody have any questions about that? Fantastic. Yeah?
If we have a for loop in Python, we can manage to write that in one line. Will there be any time difference with that one line of for loop compared to compiled version?
A one-line for loop and a compiled version? Yeah, there would still be a difference. Yeah. Yeah, the compiled version would still go faster. It doesn't really matter how many lines of code it is. Yeah.
I thought the time comes from the interpretive nature of Python, creating one line task and there. Because one line, I was thinking that that process is minimized. But compile is still.
Yeah, it still beats it. I wouldn't know exactly why. Okay, so the split, apply, combine framework is something that's everywhere in data processing. You're probably, rather than thinking about it in terms of Dask, what you've probably you might have encountered this in pandas. You may have just encountered this as the very general concept of taking a group-wise, or a very general common example of this framework is taking like a group-wise average of something. So that in that case, when we have a big data set, that has some variable that defines groups for that, and then some other variable that we actually want the average of, and we want to do a group-wise calculation. We get the average for each group, so we take this big data set and we basically aggregate it to a bunch of group-wise averages. That is sort of like the core example of split, apply, combine. And so the split step is just splitting your data set into the grouped. So you take one big data set, split it into small groups. You apply your calculation over that group, and then you have to combine those back together into a bigger data set. So that's what we're talking about with split, apply, combine. The same concept applies when we're doing data arrays that don't have any sort of like natural grouping. There doesn't have to be a column that's a group. We just take arbitrary sized slices. We just chunk it. So when we're taking arbitrary sized slices of a big data array, whether they're along one dimension or whether it's kind of a window into 2 dimensions, or whether it's a cube, or it's any sort of like slice out of a big multi-dimensional array. It's not defined by any kind of group or natural ordering. It's just what we call a chunk. So we'll just go ahead and call this framework now our chunk, apply, combine framework. So that's what we're going to do. We're going to chunk an array into small pieces, apply a computation on the small pieces, and then put that back together. And so that's what we're trying to figure out how to achieve and what Dask does for us. And when we think about what this looks like, a lot of the time it's helpful to put this into a task graph for what we're trying to achieve. And so here would be the task graph of what we did with our mean and standard deviation function. We had a random normal thing, so that was one function, that was one node in our graph, and it has the data gets passed to the next node in our graph. The data is the array, and so the data get passed over to the array. And so what we want to think about now is, all right, I want to be able to do something when array, whatever this data is that's going to get passed around, is going to be larger than the available memory on my computer. In order for this to work, we have to be able to do something with some analog of our mean and standard deviation calculation that can accurately get the final result. So like if we just applied mean and standard deviation to the whole array, we should be able to recover the value that it would have computed by doing it on intermediate chunks. So our function has to be a little smart. It has to know when I'm calculating the mean, I'm only calculating the mean of a chunk. I'm not calculating the mean. So it has to keep track of not just the sum that it's gotten or the sum of squares that it's gotten so far while doing this computing of the mean. It has to keep track of how many samples it's processed, because that information has to get passed on to our combine function, because our combine function has to know how am I going to put these things back together to accurately generate the mean of the whole array, as if I had been computing on the whole array. How do we know if something is big? It's easy when we're working with an NumPy. Every array tells you its number of bytes. So that's just there. So we can ask, that array of 10,000 things we were looking at before, that's just, 10.07 megabytes. So that's not big. Here, we'll pretend to make something that's really big by just making a big one. So we'll make a 1 gigabyte array, and we're going to start trying to do something that we'll say is very big. It's not very big, really, but we're going to pretend it's big, and we're going to sort of limit our resources that are available and sort of like see what we can do with this big array. So if we just go through and again try to implement our own serial computation, we're going to make a calculation of let's say we're going to make a calculation of a 3 gigabyte array, and we're going to do it by dividing it into 1 gigabyte chunks. So we could do that, and we could just implement that ourselves serially. We could just do it 1 gigabyte at a time. So we could generate a 1 gigabyte array, calculate what we need to calculate, generate another 1 gigabyte array, calculate what we need to calculate, do it again. So we could do it all serially. And when we do that, it takes us about almost 7 seconds to do this processing of a 3 gigabyte array when we do it ourselves. But if we think about what the task graph looks like for what we did by splitting it into 3 arrays, instead of making it serial, happening one at a time, we could think of it as being potentially parallel, because there's no reason that these chunks have to be processed one at a time. Ideally, your chunks can be processed in any order, and possibly in parallel or possibly not. And what Dask has built into it is a couple of things. Dask is a system that has the special intermediate functions that we need, applying the mean and standard deviation, as well as combining mean and standard deviation. So when I ask Dask to do a mean on an array, it does it a little bit differently than NumPy does, because it has to be able to do these intermediate calculations and then put things back together. So that's part of what Dask is. It's this collection of special wrappers around NumPy functions. It's also the scheduler. So it's also the scheduler, which is this smart system that says, OK, I know the resources that are available to you on your computer. I know how much memory you have. I know how many cores you have. And I know how many tasks, or I know the size of the task you want to achieve. And it's going to make all of the hard decisions for you, unless you want to interfere. But you can let it make all of the hard decisions for you, where it says, well, OK, I'm going to decide to break this up into this many chunks. I'm going to run them in parallel, some of them. I'm not going to run all of them in parallel. Some of them I'll finish and queue up the others for later when these are done. So it has this scheduler. And if what you want to compute on is larger than can fit in memory, it just queues them up serially. But if they're smaller than what can fit in memory, it'll do, and you have multiple cores available, it will process chunks in parallel. So it handles both the question of parallelization and delayed computation. Delayed computation where you're setting things aside until memory has freed up on your computer so that it can handle those things. Hopefully this will work because it's a little fun to see. Mostly because like once we start up the Dask client, we can do some diagnostics, which are just kind of fun to see. So we'll see if it works in real time. This client thing comes with when we imported the Dask, or we imported this from Dask when we did the imports at the top. So we have client, and we start it up, and I'll try to actually start it up here. Hopefully it goes. I did that. First little thing. Oh, well, that's OK. We'll just leave it. Warning, port 87, and said, don't worry about the warning. It's just because I already did this and forgot to close it off before. But OK, so we've started our client. We have a live client. And the fun thing here is that it gives us a button, launch dashboard in Jupyter Lab. So we look at that, and we definitely hit that button. And there we go. Now, close these things so we can get away over here. Aha. OK, so now this has loaded up our Dask dashboard in our Jupyter Lab. And anything we do requiring Dask, we'll be able to sort of see the results happening or see its performance happening in real time. So like I said, it's kind of a wrapper around things that are in NumPy. So if you know you generated a NumPy random variable, you would say NumPy random default random number generator. We just substitute Dask in at the beginning. We say Dask, that's what the DA is here. Dask, random default. The API mimics NumPy as best it can, so you have very little learning to do. So we get a Dask random number generator. And from our Dask random number generator, we generate our array. With NumPy, when we did this, we saw a bunch of numbers. With Dask, when we do this, we see this interesting widget here. This interesting widget has no numbers behind it yet. Nothing has been computed. But it tells us what it's going to be. It tells us it's going to be a 3 GB array. That's what we're going to try to compute on. It's going to do chunks of 32 megabytes, in this case because I told it to. And it tells us that this is then this generation of random numbers would have all of these chunks and then something about its task graph. It tells you a little bit about its task graph. If you ever wanted to look at it, you could. So that is there. And again, OK, so now the NumPy function is the same. I'm just going to try to calculate the mean. And it seems like it happened instantaneously, but it didn't actually happen yet. It has just looked at what it has to do. And it has figured out, OK, the result of this computation is going to be a single 8-byte number. That's all we're getting back. We're just getting back the mean. But it tells you, like, in order to do this, I've got 6 graph layers now that I have to process. So it's just got this queued up. It hasn't actually done anything. When we actually do it is when we can see how Dask starts taking advantage of the resources that are available on your computer. So Dask knows that on this machine, it can run 4 threads, because there's one CPU. I think that's what it is. I think there's one CPU that's a quad core or something like that. So it knows it can run 4 threads. And we set some byte limit on it here, so it kind of knows how much memory it can have per worker. So in this case, it's using a multi-threaded worker. You don't have to worry too much about these details, but it's kind of fun to dig into and going through it. Now, you might say, like, geez, it's taking a long time. It was much faster when we used the other one. Don't forget, we're using Timeit. So Timeit is calling this cell over and over and over and over again, which is kind of fun because we get to see these little things happen over and over and over and over again.
So what you're saying is like Timeit slows it down?
Timeit calls the cell. Timeit's actually going to call this same operation like 700 times. So it's doing this operation 700 times, the identical operation. Without Timeit, it would be done already.
Okay,
Because it would only run once. Yeah. Yeah, Ela.
When you go up and you set the client to code a little bit higher, you put the memory limit in there. I haven't seen that before. What? Maybe you said this and I didn't hear it.
I think I didn't. I think I skipped over it. But I'm just trying to do something comparable to what we did before, where I pretended I kind of only had 3 gigabytes of memory available because I chunked my array into 3 1-gigabyte chunks. Or maybe I did that wrong. What did I do? I don't remember what I did. Something like that. So I'm just trying to make it comparable to the alternative to doing a serial with 3 gigabytes as your limit. I have, however, found that by default, Dask is a little greedy. So by default, Dask will assume it has access to all of your memory. You might be doing other things on your computer. You might even be doing other things in the cloud. Dask will crash your kernel. So if you find Dask crashing your kernel sometimes, you could set a memory limit.
So you have 7.4 gigabytes there, I see at the bottom. And so by saying 3, you are saying you only get to use 3 of those.
Yeah.
Okay.
Why do you need to run the same operation 7 times?
To get it.
Ways, or is the same operation done 7 times?
Yes, but every time the computer does something, it actually takes a little bit of different time to do it. So we actually want some statistics on how long it takes it to go. So I could use, there's a simpler magic % time, and that just gives you the wall clock time for how long it took it to go once. And it's nice to run it a bunch of times because you actually get that plus or minus this many seconds on how long it took, because there is real variation in there. Time iterate, is that what it's called? Okay, yeah, there you go. Yeah. Okay, so, and then, yeah, we got our result. That took 6 seconds. What did we do before? Before, it was 8 seconds. So we basically, we achieved the same thing here, and we didn't speed things up a whole lot compared to just using our own sort of basic serial implementation of chunk apply combine while giving all of the memory available to a single step in my task graph. So we didn't see a huge speed up here. And that's an important thing to note, is that Dask is about scaling your processes up to bigger resources. So when it doesn't always make everything faster. It's not always the go-to solution to just make everything faster. It's about splitting your processes up so that bottlenecks don't slow you down. And we'll see a bottleneck later on probably. It's about splitting your processes up so bottlenecks don't slow you down, but also being prepared and ready to scale up for larger computing when available. So when you do need to scale your computing up to a cluster, it's the same Dask commands. So when you can actually do have access to resources that you would not be able to take advantage of on your own, Dask can do that for you. It can scale. It can run this task graph on a whole cluster of machines. It can run this task graph on a machine that has a whole bunch of different things. It can run a task graph with a Slurm controller. It can send jobs to Slurm for you if it needs to. So it has a very good ability to help you distribute once you learn how to use it. But it's not necessarily just going to when all you have is one computer with 4 gigabytes of memory. It's not magically going to make things like a lot faster. But it's good to know how to use, because you might get there.
Is every NumPy operation represented in Dask?
That's the goal. I can't say for sure if everything is. I haven't encountered something that's not.
Can you import Dask and call it NP?
And most of your code would work. Okay, enough hokey examples. Let's try to actually generate some data. What we're going to try to do is, oh yeah, well, hold on, let me stop. We just had some questions, but I'll pause and see. Are there questions about the concept of Dask? We're going to just try to use it in the background now. Are there questions about the concept of Dask or what we just went through? Yeah.
So it looks like part of what you're doing is you might have like a big data set and you split it into like smaller pieces to do operations on. Could you use this like if you have a data set that's too big to load in the memory to have it like just like small operations without having to load the whole thing in memory?
Yes, exactly. So that's where it doesn't necessarily speed us up. So we're going to do something now where we only have one core. We're not trying to distribute across a cluster. But the advantage of using Dask in this situation, where we're still only using one machine, is yes, it can do things in parallel, but it can also do things delayed. So we'll act like our computation is something we can do all at once, but the Dask graph will then start happening serially instead of in parallel. Yeah.
So Dask can only do things that NumPy can do. For example, if there's something else I want to do, and I want to put it in different processors, or I want to take different nodes in the cluster, can I not use Python there? Because usually we use shell for that. So.
You can define your own functions, and use Dask to map those functions over chunks arbitrarily. So yes, by default, it can do most of the stuff NumPy does, but it also has Dask map, and Dask map lets you provide the function, and you have to be pretty clever to get that function to work right. But it can then map that function. It can chunk the data you're trying to operate on and map your function over those chunks. Yeah, so you can supply a function. Is that the question?
Yes.
Okay.
Maybe this is going to be in this part, but if you're chunking your data, or like you have your own function, how is this different from like, I wrote something, but I'm using multi-processing? I don't know, I just picked one, but like, can you do the same thing with Dask, or like, is one better than the other, or?
I won't venture to say whether one is better than the other. At some level, Dask behind the scenes is using a native Python library, and I'm not sure if it's using multi-processing or there's another one called concurrency, I think is the other one. Concurrent, maybe it's called concurrent. I'm not sure which Dask is using in the background, so in some sense, you may be doing just like the lower level implementation. What Dask provides a lot of the time is this native interaction with Xarray objects, which we'll kind of see a little bit more here too. So it should be easier, is the idea, than implementing something with multiprocessing. But if you know what you're doing and there's low-level things you need to tweak, by all means, it probably might be using multiprocessing in the background. There's some tricky concepts in this. Like I've probably made mistakes of going back and forth between using the words processes versus threads. These are different ways of using your CPU in parallel. And they have different implications for how memory is shared between things. And there's some subtleties here that you'd have to take a computer science course to really sort of like be an expert on. And so hopefully Dask handles some of those complexities for you. All right, let's stack some data. And we're going to do this fairly quickly, mostly because I'm not really sure that I've done the most intelligent implementation here. But there's some things that I want us to see, sort of like, because this kind of sets the framework for what are the steps we go through when we really want to, when we want to project our data to something, to a specific geolocation array, or a specific coordinate reference system. Here's one way we can do it. So one thing we do is we use PyProj to help us with the coordinate reference systems. These things are all in a big database. They have codes. We don't write into our level 2 data files the coordinate reference system. You just have to know that it's, you see lat lons, you know that it's not the 80s anymore, so we're using WGS84. So like that is the coordinate reference system that you should default to, and that's known as 4326. So this is just one of these things that geospatial data people know. Oh yeah, 4326. So we'll use that projection. That's the WGS84. Sorry, not projection. We'll use that coordinate reference system. That's the WGS84 geographic two-dimensional coordinate reference system. That's your lat and lon. What we can do is we can ask PyProj, like, OK, well, given that I'm interested in this small area over the Chesapeake Bay, and I think I want a UTM projection, which one should I use? They're all numbered, like up through 20 or 20, I don't know. So PyProj will tell you. You can look it up. You can give it your area of interest. And say query the UTM coordinate reference systems, and it says use UTM zone 18 north. Great, OK. I'm going to project to UTM zone 18 north. That also has an EPSG code, et cetera. It's important to note when you're playing with these things that the order of axes is defined in these sorts of data things. So this is easting and northing. That's the order of you get. You get X is easting and Y. For the other one, you get latitude, then longitude. You get north-south, then east-west. Don't swap those. It's easy to do. We'll use PyProj to make a transformer that can go between these things. And then we have to start transforming things. So we transform our bounding box. So we go between meters in UTM north to lat-lon degrees. And so this is all the database stuff that PyProj does for us. We can transform things. We can develop a new data array that's going to be our gridded output. So we develop a new gridded output. We have X and Y now instead of lat and lon, and these are in meters. But it doesn't have any data yet. So we're sort of going to define our area that we're going to project into, and then we're going to do the projection step later on. in order to use, okay, so more transformations. So now I'm actually transforming the latitudes and longitudes of our grid points. So I'm taking our grid points in meters and converting those to latitudes and longitudes so that we have that data variable available, because we're going to need to compare against those gridded latitudes and longitudes and pulling things out. Let's actually look at our data now. So I'm just going to open 10 of the results that we got before. Remember we had all of the granules that intersected the Bay Area up through July, the end of July. There were some 200 of them. So we're just going to open 10 of them so that it doesn't take all day. It took about, when I actually ran it, it probably took about 5 minutes. We're going to use OpenMF dataset, and I'm going to kind of gloss over this, but it is important. It's useful. Those two little functions I defined above, time from attribute, we can use these as preprocessors when we're using OpenMF dataset to come up with multiple files. So OpenMF dataset will handle all of the paths we give it. We open multiple files at the same time. But in order to get these things stackable, we want time in there as a dimension. So this little preprocess step allows us to do that. And what we come back with is a big stack, but it's unprojected. So it's time. It has 10 time steps in here, but it's still number of lines, pixels per line. So we've got this time dimension and then numbers of line, pixels per line. So everything's the same shape here. It's a nice cube. It's just not projected. So we're going to have to individually project each layer, and then we'll find out if they overlap or not. So we're going to load up a client. Let's see if that went. That one went. And, ooh, I might have overwritten my data set. Let's see if this works. All right, we're going to load up our client, and then we're going to do a big loop. This was kind of my first indication that, like, I'm not doing this right because I'm actually still looping. I ended up grouping over time to do this. But the main thing that happens here is this grid data function. This is called to SciPy. This is called from SciPy. And it takes the latlons that we have in our swath, the data that we want, which is chlorophyll A, and the latlons that we want to project to. It takes those three arguments and gives us back the regridded data. And everything else that's in here is just about swapping dimensions around and manipulating labels in our data sets and putting things so that they can be assembled back together. This grid data thing is really the key thing. All right, did we get our data set? OK, I have a data set. Oh, OK, right, so the important thing. So far, I haven't done anything with Dask, as far as you can tell. I haven't said anything to Dask other than opening up the client. But I used OpenMF dataset to open multiple data sets. And this automatically triggers Xarray to use Dask back-ended data sets. If you look at the output in this nice little handy graph, in this interactive little visual output that Xarray gives you, all the data sets here are these funky Dask chunks. And it tells you how it's all chunked. So where's chlorophyll? Chlorophyll is right here. It's lazy. It has not been read into memory yet. It's still sitting in S3 buckets, but we know how big it's going to be, and we know how Dask is going to chunk it up. So I can make sure my Jupyter dashboard's connected. I think it still is. And see if we can fire it off. Does anybody else ever get their notebooks frozen? Sometimes it freezes for me for a couple seconds.
Every time I run that command, it says your kernel can die.
My kernel hasn't died. It's just the interface is freezing.
You can't click or highlight.
You can't click or highlight anything?
Yeah, attach and replace.
I think there's a reason for it. I forget what it is. I don't run into it much.
Yeah. I don't run into it much. It's very random.
It might be large notebook or the way that the imaging of the notebook on Jupyter has.
Yeah. Well, OK, it's not going to let me run right now. So what we would see is we would see all these Dask things fire off, and we'd see a lot of processing happen, and then we would see nothing happen. And that nothing happening is while it's waiting to get data from S3. And then a whole bunch of processes would fire again, and it would start going, and then nothing would happen, because it's trying to get data from S3. And it's that's a kind of an important concept in performance. That's bottlenecking. So you're bottlenecking on loading the data. So there's probably some smarter ways to do that too, to sort of like make that more continuous so that there's some data loading happening and some compute happening at the same time. But there's always going to be delays reading from S3. It's not instantaneous. There's going to be delays there. So just that would be what you were seeing when it looked like Dask was not doing anything at all.
When you're saying you're waiting for it to load from S3, that's as you're pulling the data finally from the cloud, the Cloudworks, so it's not like
Yeah, because I used that Earth Access open. All I did was establish a link to the data. So I got it. I know where the data is. I haven't actually pulled any of it to S3 until I start doing the computation.
if you're doing it on like a local machine, would you still see like the eye or something? Would you see that type of
Probably not. You'd probably get almost no latency from reading from your local hard drive. Yeah, local hard drives are pretty fast. Oh, it still won't let me do it. Shoot. OK. Well, what it would do is it would give us our coordinates back. And what you would see when you plotted your nice figures is that you had nicely projected your level 2 data to this region. So this was the region we projected on. And you would hunt through these images. So right now we did 10. So you'd have 10 of them. And sometimes you would see one that had a nice image of the chlorophyll data that you wanted to see for the Chesapeake Bay. But a lot of the time you'd see that, oh, I was on a swath edge. Because remember, the bounding box, when we do our search, that B-box argument is anything that intersects, any swath that intersects this bounding box is included. So this was a swath that's like mostly over here. We just got the edge of it, but it still shows up in our data. And for what you're doing, maybe this is good. Maybe you wanted part of the data here. These are not going to be regularly sampled in time. We asked for anything. So if I plotted a time series of a particular point in here, you'd see like you probably get data sets. You'll get like 2 hits 10 minutes apart from each other. Because you're going to get, there's going to be the times where the instrument was going like this, and then the swath ended. Time when the instrument was going like this, and the swath ended, and we started another swath right there. And so you'll get that one, and you'll get that one. So you'll have 2 data points right next to each other in time. But you've got it all now, and now is when you start figuring out what's the next. You can plot it all in 2 dimensions and say, like, OK, well, what's the next step in doing my analysis now that I've got everything gridded to the same level? And when we do this with the level 2s, we get the advantage of we can get it to the finest resolution we trust. It's not necessarily the aggregated resolutions that we get in the level 3s distributed by the OBDAC. So when you want to look at something closely, it's a good skill to know how to do. Maybe it'll fire while I take some questions. Is it going yet?
If you click another cell, mine just froze. I clicked like the one I did before, and then it froze.
I'm also just refreshing. We'll see if that does it. Questions?
Okay, so when you open a data set, an X-ray data set, and I'm opening like the Chlorophyll A1, and it has Dask graph, it says 70 chunks and 39 graph layers. What does that exactly mean?
You just opened it, and that's what you see.
Yeah, like I expanded the little cylinder under Chlorophyll A, and it says why 70 chunks?
So one question is, I think, how does it decide natively what chunking to use? Yeah. And chunking is built into the way data is stored in NetCDF files. So when data is stored in NetCDF files, it's not always. In our data, it is. In most data, it is. It's chunked. So it's actually stored in chunks and compressed in chunks. And so when Xarray reads it, it's actually probably mimicking what it finds in the data itself. So it's probably choosing chunk sizes that correspond to what it sees in the data file. So it picks that up in the data file attributes. So that's part of the answer. The graph layer is, who knows? Dask does all these funky steps to load data, and like that graph is how it keeps track of everything it has to do to get the final data product. If you wanted to inspect it, you could. You could see what that graph is, but don't bother. Yeah, we'll go over here.
So, question about the automatic chunking. So, if you were to load something and have it auto chunked, and then you were to slice down to a smaller area, would it then redo that chunking to make sure that it's optimized the chunking within that? Because what happens if it's cutting something with 2 chunks, but it could really re-chunk it? Is that something you have to specify so that it re-chunks, or is that something that you just have?
I'm not totally sure, but what I've seen is that Dask will try to preserve the chunks size as they are, but there will be certain operations, and I'm not sure. I think it does it can be like select operations, something that does slicing, will trigger a warning sometimes that you'll actually get a warning on your screen that says this operation is causing a very large chunk to form. Is the one I've seen. So it does change chunk size, and it tends to warn you if it thinks it's doing it in a bad way. But I think if it goes from one chunk size to a different chunk size and it's still okay sizes, you might not even notice. That's not the most satisfying answer, but yeah.
This is another, I guess, more like functionality question, which you could probably figure out online. But like if you're running something over and over again, but you want the output of that data to like go into an array, but when you split it, it's kind of randomized. Like, can you use that for that, or do you just like run the function and then afterwards, like, I don't know.
I don't think I understand the question.
Like,
You
if
want
you
to?
wanted to run a function on like each point on the grid or something, and you could do it all the way, but you want to preserve the locations, like maybe.
If you can keep your object as an X-array object so that it has the coordinates and dimensions attached to it, and use Dask on that X-array function, on that X-array object, everything should be preserved. If you have to extract out the basic array with nothing else around it, then you would have to re-add the labels back in. You'd have to re-add the coordinates and the dimensions back in, if that's